Good morning. Today I'm going to present even and odd function. That will be our first topic. I'll present more than one topic. These are linked topics. So here we have to classify a function as even, odd, or neither. This classification can be determined graphically or algebraically. So before we even go there, let's discuss what we know about this topic. So because we have done it before. So let's say we have y equals to sine x. The graph of y equals to sine x, this is how it will look like. Okay, so this is pi, and here is also pi, negative pi. So basically what they're discussing here, if you look at this function here, this is 0. If you are at 0, you look up and you look down, you see the same thing. Okay, so this type of function, we say that they are symmetrical about origin. They are symmetrical about origin. And if we have this function of cos, y equals to cos x, the graph starts at 1 here. Let's say this is 1. I want to plot it in such a way that it's going to be symmetrical. Okay. Let's just plot it up to 190, up to 180. So this is pi, and this point here is negative pi, like this one. So you can clearly see that this is our y-axis, this is our x-axis. This graph is symmetrical about the line, the y-axis. So if you are on the line, this y-axis, you can, when you look on the left and you look on the right, you see the same graph. So this is an even function. This one is an odd function. Okay. Another way of seeing that function is even. Let's say you have y minus x is equals to, in this case, is equals to sine x minus x, and this is equals to minus sine x. For this one, y minus x is equals to cos of minus x equals to cos x. So this is another way of testing that the given function, this is called algebraic. It's another way of testing that the given function is even or odd. Okay, now let's just go through the document now, because the document is clear enough. Now, the first method is graphical interpretation. Even function have a graph that is symmetric with respect to y-axis, and odd function have a graph that is symmetric with the origin. That's the point I've just discussed there. So let's look at these two graphs. This one here, you can see that it's symmetrical about the point, the origin. So if you at the origin, you look down or you look up, you see the same graph. Okay, if we were to flip this one upward, we'll have the same graph. Okay, this is symmetrical about origin, and this one can see that is symmetrical about the y-axis, x like a mirror. Okay, if you spin the picture upside down about the origin, the graphs looks the same. That's what they're discussing there. So this type of a function is odd, and this type of a function, this one is even, this one is odd. Odd, even. So you can be asked to identify these graphs graphically. And then algebraically, we have just discussed it on top. Substituting minus x in for x everywhere in a function and analyze the result of f at minus x by comparing it to the original function fx. If you end up with this, we see those one in green, we conclude that we have an even function. And if you end up with this one here, we conclude that we have an odd function. So this is how you do it algebraically. Let's see example where they have done it algebraically. Number A, you substitute minus x where you have x, you have minus x, and where you have x, you substitute minus x, and simplify. Minus, if you square this, you end up with x squared plus 4, which is the original function that we started with. So substituting minus x doesn't change anything, it remains the same function. So this type of a function are even. Now here, we substitute minus x here, we simplify. After simplifying, you are able to take minus 1 out as a common factor. And what we have inside the bracket is the original function. So it's the original function multiplied by negative. We have minus fx. So if we have such situation, then we have an odd function. Now, if you look at this function, the last one, number C, we substituted minus x wherever we see x and simplify. We end up with x squared plus 3x plus 4. Is this the original function? The answer is no. This one is positive, that one is negative. So we conclude that minus, if we substitute fx, we do not end up with the original function. Now, if we substitute minus x, do we end up with the original function multiplied by negative? Let's check that. If we take out the negative out on this one, we have minus x squared minus 3x minus 4. Is the function inside the graph the same as the previous, the original one? The answer is no. So we conclude that this one also is not equals to minus fx. Okay, now if we have this situation, then we know that the given function is not odd and it's not even, it's neither. So that's what they are discussing here. The first one is even function, odd function, and neither. That's basically what I wanted to lecture under odd function and even function. If you can do this, then you're done. Interpret it graphically and interpret it algebraically. Then I think you'll be sorted. Then under here, these are questions, so you have to answer them. I'll upload this on my YouTube. Luckily, they have given you answers, so it's answers only. So you have to prove that there's the answers for the above 1, 2, 3 up to 10, but you must solve to show that the answer is indeed even. Okay, whether you plot the graph or you solve it using algebraically. So you have to substitute minus x and simplify and see if that is the case. I'll leave it to you to do that. It's your homework. Okay, now let me check my notes. What do I have to discuss next? What I'm going to discuss next is periodic function. So luckily, periodic function relates to sine x and cos x. Sine x, this one that we have on top here, this sine x. I'm going to show you a slide. Yellow?
Sorry to be bothersome, but can you please repeat the graphical interpretation?
The graphical?
Before you move on. Yes, just the graphical interpretation.
Okay, the graphical interpretation. Which one would be easy? Okay. Y equals to x to the power 3 and y equals to x squared. So if you can graph these two graphs for me, because this one is standard graph, we know how to play. I think this one actually, it might represent y equals to x to the power 3, this one that we have on the left. How will it look like? I think it's similar to this one. We'll check that. Y equals to, this is y, this is x, so this is y equals to x to the power 3. Okay, now this function we say that is odd about, is symmetrical about origin. Okay, so this means the same graph that we have plotted here on the on the y-axis, you'll plot it, but now this time is facing downward, not upward. Can you see that? Moreku?
Yes, sir.
Yeah. So this clearly shows that this is symmetrical about origin. But now for x squared, y equals to x squared. This is it's like you looking in the mirror. What you see there is what is a mirror image of you. So the y-axis actually acts as a mirror. You see the same thing. Okay. So this one will basically be an even function. Okay. So basically that is that. You must be able to interpret in that way. But I'm still going to cover it again. It doesn't end here.
And
so when I'm
how are you able to tell when it's neither odd or even?
Either odd or even.
Yes.
What, graphically?
Yes, sir.
It must fail both symmetries. It must fail the even part and the odd part. So the function must not be symmetrical about the origin, and the function must not be symmetrical about the y-axis. Then it fails the requirement. Any function that fails the requirement is not even and it's not odd.
Okay, so that's clear enough. Thank you.
Okay. Okay, now what I'm going to discuss next is what is periodic function. Okay, a few minutes, I'm coming. Hello, I'm back. I'm doing two jobs at the same time. So what I wanted to discuss here before I go that side, before I go and copy, sine. We know the period of sine x is 2 pi, and the period of y equals to cos x is 2 pi. So this is how we write it. F x plus 2 pi is equals to fx. Okay, so this basically they usually represent it by t. So this is the period of this function. Okay, so we know that the sine graph is repeating itself after each and every 2 pi. Okay, so it's the same graph repeating, isn't it? Okay, after 2 pi. Now, can we go and discuss that now? I'm going to leave this one, and then we go to periodic function. Okay, this one we have discussed the wholes and the poles and the zeros. It's under polynomials. Now, in this slide, I'm going to discuss only two things. You should be able to define or explain the concept of periodic functions, sketch and specify the number of cycles of the periodic functions. Only two things that I want from you. Okay, ignore this one. Now let's define. A periodic function repeats itself at regular intervals. Mathematically, we write it in this fashion. F at x plus t is equals to fx, where t is the period of fx. This is what we have just discussed, okay? So t is our period. Okay, now let's just look at this sketch here that we have here. Let's look between 0 and 1. From 0 to 1. You can see that we have one cycle and it's repeated 4 times. Okay, so this means we have 4 cycles. It's 1, 2, 3, 4 cycles. The same graph repeated 4 times. Okay, the period of this one is t equals to 1. Okay, so if I were to write it in this fashion, it's going to be f of x plus 1 equals to fx. Okay, where 1 is what is just our period. Okay, now let's discuss this function, why fx equals to cos x. We said the period is 2 pi. It's well known that the period is 2 pi. Our function starts here at 0 and ends at 2 pi. 2 pi will be here. Then after that, we just repeat the same thing many times, okay? So this is our function fx equals to cos x. Similarly, sin x, it's got the same period. But now here we are not given sin x, we are given sin x equals to 2t. Now, we know that t is equals to 2 pi over omega. Now, in this case, this is equals to 2. So we have 2 pi over 2, and this is equals to pi. So our period is pi. Okay. Now we have tan x, and if you check here on top also, I didn't see that they are asking if the given function is odd or even or neither. You have to check that. So the answer here, it will be an odd function. Okay, now let's just discuss this one. It's got the tan x, it's got an asymptote at what? How do you get this asymptote? I'll show you now. These are the asymptote we are talking about. Vertical asymptote. We know that y is equals to sine x over cos x. So you look at the values where cos x is equals to 0. So cos x is equals to 0 at what? At pi over 2. So this point here, it will be pi over 2. And this one, it will be negative pi over 2. Those are your vertical asymptote. And another thing, you substitute minus x here on this one. Okay. My conclusion is that it's an odd function. Based on this one, it is symmetrical about origin. Okay. So at some point we should discuss the properties of even and odd function. So using one of those properties, that we have an even an odd function divided by an even function, the resulting will be an odd function. So when you get home to the as a homework, for you to be able to answer this answer algebraically, you need to know the properties. You have to check that, the properties of even and odd function. You can check this one on the internet, on YouTube. So my conclusion here, based on the graph, is that fx equals to tan x is an odd function. My decision, I take it based on the graph. The graph between minus pi over 2 and pi over 2 is what? It is symmetrical about origin. Now the question is here, is this function periodic? The answer is no. The reason being that we have two different graphs here. Do you see this? They are not the same. They're supposed to be the same. So is here. No, the left plane differs from the right plane. You can see these two are different. They are not the same. So it must be the same graph repeated on a certain interval. Maybe it's from 0 to 2 or 0 to 2 pi. That having such interval, okay? Having an interval of 2, it repeats on that interval of 2. Now, is this function periodic? The answer is no. The reason is being that you can see that these two functions are overlapping, this one here and this one. And even this side, this one is overlapping in this, are not the same interval. So this is not the same interval. Yeah? And Ndlela.
Sorry, sir.
I thought you were asking question.
No.
Okay. So switch off your mic. Okay, so these two are actually overlapping. So if you have this situation, this is not a periodic function. Okay. Now let's discuss this one here. What is the period of this one that is given here? We are given that the period is equals to pi. But originally we know that the period of sine is 2 pi. So this means we are only going to plot the graph of sine from 0 to pi. Okay? Because we are doing half of the original one. Okay? So it's even the domain is here. They are restricting you to plot this graph from 0 to pi. Okay? Here they're explaining that the period of this function is 2 pi, and in the shorthand is 2 pi. Then what is the meaning of that one? Okay. Now, like I said, now let me show what I was talking about. Let's take this one to be 0, this one to be pi, 2 pi, 3 pi. So in the next one, negative pi, negative 2 pi, and negative 3 pi. So how does the graph of sine look like between 0 and pi? This is the shape of the graph. Now this graph that we have between 0 and pi, we are going to repeat it on those intervals. So this is what they're talking about. The graph is repeating itself after each and every pi because our period is pi. Okay, so similarly it's going to do that this side. You must plot it accurately. This mine is not accurate in this case. Okay. Okay, now let's see what the solution they have here. They have solution. So here they have plotted only 3 cycles. The first cycle starts from 0 to pi. So they repeat it 3 times. Okay, so if you have this information, it's actually restricting you to plot the given graph according to that period. Our period is pi, not 2 pi as the usual one. Okay. Now let's see for cos. For cos, they are restricting to plot this graph from 0 to pi. Now let's look at the graph of pi between 0 and pi. So this is 0, and this point here, make it pi over 2. This one is pi. So my graph will look like this between those two coordinates, between these points. Okay, and then from there you repeat this graph that you have between 0 and pi. So you can do that, you can repeat it to show that it's a repeating function. So this is minus pi over 2, this is pi, and here you will have 3 pi over 2 and 2 pi. So this will be your x, and this will be your y. So you can see that the same function is repeated 3 times on those 3 intervals. So like in the previous example, this is restricting, you are plotting from 0 to pi, not the usual one from 0 to 2 pi. Our period is pi. So this is the accurate one, the correct, the well plotted one. There you can see the from 0 to pi. This is the graph that we have. This is the original one. Then from there you repeat it on given interval until the required number. If they require 5, then you must plot it 5 or 3. Okay. Now, the next thing that we have to discuss is half range functions. So these things are very important. Next, at some point, we'll be dealing with what we call, I'm actually doing foundation for what we call Fourier series, which we'll do next year. It will require you to know what is an even function, what is an odd function, what is the periodic function. So it leads you to somewhere. Okay, so if you know that the function is even or is odd or is odd, it will actually reduce the amount of work that you're going to do for computation to determine that series. Okay, so it's important. And then this half range function will also appear there under the Fourier series. So you must remember that. So G, here we are given that G is equals to T squared, and this is the domain. We are restricted on this domain. You must plot this graph from 0 to 2, okay? And then we are given that the period of this function is what? Is 4, okay? The period is 4. Now, this is called half the period. We are plotting G on what? Half the period. And G is called half range function. And then for us to be able to plot this type of graph, we need these two things. We must clearly tell us what type of a graph are you looking for. Like for instance, if I were to plot this one here, I'll plot, let me use a different color. I'll plot first from 0, this is 0 to 2. That's the first thing that I do. I'm plotting this one, this 2. I'm using this 2. It gives me this one. Now, they might ask me that the function must be even. So if they are looking for an even function on the period of 4, so I'll plot from 0 to 2. I've done that already. Now I'm following this even. How can I plot this function in such a way that I end up with an even function? So I plot the same graph. I'm going to plot the same graph this side from 0 to -2. And the period is what? The period is 4. From 2 minus -2 will give you 4. So it's still under this one. Okay, then from there they say repeat, give us 3 cycles of this type of a graph. So now you already know now. You plot it from 2 to 6, and you plot it from -2 to -6. So now you have 3 cycles. It's 1, 2, 3. Now, this is when they want an even. If they want an odd one, they tell you that they are looking for an odd function. I wanted a different color. If they are looking for an odd function, so you have already plotted from 0 to 2, 0 to 2. This is the function. Now you want to plot it, the odd one. So you can clearly see that you'll plot the same one, but it must be symmetrical about the origin. Okay, so now this is the first cycle between minus 2 and 2. You repeat the same function 3 times now. So this will be 6. This will be 6. And it must pass at 4 here. So you plot something like a parabola, one side of a parabola, even here. It's not clear. Okay, let me start from this point to show you that. So you plot this, and this one also, it must be like this. Just wanted you to see it. So this one comes, wait. I'll change those numbers, it must be clear. So this is minus 2, this will be 4. And this part here, it will be 6. So we have 3 cycles from, this is 1, 2, 3. Okay, and this is the, this is T and this is GT. Okay, now let's look at it, how they have plotted it. So this is the same what I was trying to do. They ask you to plot 3 cycles of even GT. So you first plot this function, this one here, like I did. You plot it from 0 to 2. And then from the word even tells you that you must reproduce an even function. That's what they have reproduced there. You have an even function between minus 2 to 2. Then from there, you repeat that function again there. In this side, from minus 6 to 2, from 2 to 6. Who's making noise? I must give me a platform. You want to ask question, Motlala?
No, I'm fine.
Okay, switch off your mic then. Okay, so basically that's how it repeats. So for this type of question, you'll be given these intervals from 0 to 2 and a period, and they must indicate to you what type of a function they are looking for. Is it an even function or an odd function? So you start first by plotting this graph between 0 and 2, and then because they are looking for an even function, then you must plot it in such a way that it is symmetrical with the y-axis. So if it's symmetrical with the y-axis, then it is going to be an even function. And then from there, they say plot 3 functions, 3 cycles, not function, 3 cycles. Then you plot those 3 cycles. This is the one, 1, 2, 3, okay? So you can expect this type of equations anytime, okay? But mostly I'm doing it for next year. Even if you don't get it in the test this year, but definitely next year we'll use it. So here, you check the domain. You start first by drawing this graph between 0 and 2. Then from there you follow. They were looking for an odd function. So you plot it in such a way that you have an odd function. You can see this one in the center. It's actually symmetrical with origin. This is one cycle from minus 2 to 2, and our period is 4. You can see that 2 minus minus 2 will give you 4, our period. This is one cycle. Then you repeat that. We have another cycle here and another one here. Okay, so this basically ends our periodic function. The remaining ones is just a repeat of what we have covered. Let me explain this one. This one is what we call a split function. So this is similar to fx equals to, let's say, this t, the absolute value of t. You can clearly see that we have plotted that absolute value of t between minus pi over 2 and pi over 2. You can see this in absolute value. Okay, then from there you just repeat it. Okay, this one basically represents gt equals to minus t, and this one represents gt maybe equals to t. So you can see this is basically an absolute weight graph. You plot it between minus pi over 2 and 0, between 0 and pi over 2, and then you repeat it. And the t equals to pi. You can see that if we have pi over 2 minus pi over 2, this will give you pi. So you can clearly get the period from here, the distance from here to here. It will give you pi. Okay. Now, what I'm going to discuss next is what we call continuity. We have discussed that before. So this is what we are going to do. Continuous or piecewise continuous functions. So let's discuss this. So the first thing, we have discussed continuity before. So this is just a statement. It says that in mathematics, the term continuous has such the same meaning as it does in everyday use. To say that the function is continuous at C, it means that there is no interruption in the graph of fx at C. The graph of fx is unbroken at C. There are no holes, there are no jumps or gaps. As simple as this concept may seem, its precise definition eluded mathematicians for many years. In fact, it was only found in the 1800s. Okay, so now, in the previous class, we discussed what is continuity. So a function fx is said to be continuous at the point x equals to a in its domain if the following three conditions are satisfied. The first condition is that f at a must exist, and the limit as x approaches a of fx exists, and the first bullet and the second bullet must be equal. If they are equal, then we conclude that fx is continuous at a given point. Okay. Now we have these examples. They say discuss the continuity of each function. According to me, this question is similar to determine the domain. So let's determine the domain of this function. What is the domain of this function? The domain of this function is x, an element of real numbers. So basically this function that is given here is continuous everywhere on the system of real numbers, everywhere. The second one also is basically continuous everywhere. Now looking at this one, discuss the continuity of each function. So for this one, we look for the domain. What is the domain? The domain of this one, x must not equals to 0, and x is an element of real numbers. So this given function will be continuous on this domain. And this one we can simplify it as x plus 1, x minus 1, all over x minus 1. So from here we can say that f has got removable discontinuity. So we can remove the discontinuity, and its domain is x. Let's see here, x not equals to 1, and x an element of real numbers. So this function will be continuous in this given domain. The last one we have already discussed, x will be, it will be continuous everywhere on the real number system. So you should be able to determine the domain of a function, and after that you describe the continuity of that given function. Now we are going to what we call piecewise continuous function. So we must be able to draw their graphs and discuss its continuity. Is it a continuous function or not? Now here they ask you to discuss the continuity of this function. So the discussion is below. It consists of three continuous pieces separated by finite discontinuity. Note that the function need not be defined at the endpoints of the pieces, only the limit needs to exist. Okay, so for us to discuss this continuity, basically we are going to look for FA, the limit as x approaches a of fx, must know it, and then we must prove that FA is equals to the limit as x approaches a of fx. So if we have these 3 points, then we can conclude that the graph that we have above there, here, something like this, is continuous. So we have to prove these 3 points. Then we conclude that the given function is what? Is continuous. Now let's start with this one. Let's discuss the continuity of the following function. Okay, like I said there, now I'm going to determine the limit. Let's determine the limit as x approaches -1 from the negative side. In this case, if you look at this split function, at this point our function will be equals to fx plus 3. And then we look for the limit as x approaches -1 from the positive side, and we have x to the power 3 plus 5. Now substituting -1 there, we end up this is equals to 2, -2. And substituting -1, this is equals to 4. Now the fact that our limit at -1 is approaching 2 different values, we conclude that the limit does not exist. The limit does not exist. So we conclude that the given function is not continuous at x equals to -1. So this given function is not continuous at x equals to -1. So that's our conclusion. Now let's look at the second one. What do we do here? Let's start by determining the limit as x approaches 3 from the negative side. We have 3x minus 2, and our limit in this case is equals to 7. We look at the limit as x approaches 3 from the positive side. We have x to the power 4 minus 74. This is 81 minus 74, which is equivalent to 7. Now, we conclude that the limit as x approaches 3 of fx.
How do you get the limit as equals to 7?
You substitute 3.
Okay.
Yeah. So this limit, the limit as x approaches 3 of fx is equals to 7. We have determined the limit. Okay. Now, if we determine f at 3, so we substitute on the first equation 3. 3 minus 2, our answer is 7. If we substitute on the second equation, this one, we have 3 to the power 4 minus 74. This is equals to 7. So now we can clearly see that the limit as x approaches 3 of fx is equals to f at a. Now, by the definition of continuity, we conclude that the given function is continuous at x equals to 3. Okay, can conclude there. The given function fx is continuous at, I want to use a different color. Fx is, let me write it nicely now. Fx is the right way is to write like this. Piecewise continuous. Continuous at x, continuous function at x equals to 3. Okay. Now, this one, they say discuss the continuity. I'm just trying to reinforce the previous one. Let's check this one. We have to check the limit. The limit as x approaches 1 from the negative side. What is our answer? This minus x squared minus 4. It will give us what? If we substitute 1 here, is minus 5. Yeah? And the limit as x approaches 1 from the positive side, we have x to the power 4 minus 6, and this gives us minus 5. So we conclude that this the limit as x approaches 1 of f at x is equals to minus 5. If it exists, then it's equals to minus 5. Now f at 1 is equals to minus 1 to the power 2 minus 4, and this is minus 5, and f at 1 again there is equals to 1 to the power 4 minus 6 equals to minus 5. And from here you can clearly see that the limit as x approaches a of fx is equals to f at a. So by the definition of continuity, we conclude that the given function is continuous at x equals to 1. Remember, our a here is 1, isn't it? So when I write a, in this case is 1. Okay.
Oh, sir.
On the do we substitute minus 1 or 1?
It's 1.
Because I see minus 1.
It's 1, sir.
Thank you.
Okay. Now, the other thing that is important is you should be able to graph this type of a function, this split function. Okay, so I'll follow the steps. So let's plot this one. Okay, the first step, what I want to do, if I want to substitute 2, because we can see this 2 is the interesting point here, is the critical point actually. So at 2, our function is equals to what? I think it's minus 5. So it's 1, 2, 3, 4, 5. This will be minus 5 here. You can just write it down here. Okay. Now immediately after that, I want the x-intercept. The x-intercept will give me minus half. So I choose this point here to be minus half. And then the y-intercept is minus 1. I choose this point. So we have 1, 2. So the function at that point is minus 5. So it will come this way, pass through that point up to this point. Then it can go up. I don't know where it's going to stop. So this is y and this is x. So we have plotted the first graph. We must plot it less than 2. Less than or equals to 2. The second one, I substitute 2. My answer is 2. This means at 2, this 2 here is 2. The answer is 2 is 1, 2. So it will be this point, this open. Okay. Now my x-intercept. My x-intercept is 4. My y-intercept is also 4. To be that point there, but we're not going to use it because we must plot our graph above where x is greater than 2. So we are not going to use that. So this means our function must pass through x up to infinity there. Okay, This point that we have from this point here to that point is what we call jump discontinuity. We have a jump discontinuity. Let me show you by highlighting it. You see this space here from this point to this point. This is our jump discontinuity. Okay. We have a jump discontinuity. Okay. So we have managed to plot the graph. Let's plot another one. Now they ask us to graph this one. Let's see how we'll do that. We'll follow exactly the same steps that we have used in the previous one. Okay. At -2, let's see, our critical point here is -2 and 2. This is -2. At -2, our function is what? 1, 2, 3, 4 is -4. Our function is -4. Okay. Now let's look at this, the second function. If we substitute -2, our answer is it -4? Yeah, it's -4. Now let's look for x-intercept. Our x-intercept is 2. So this will be 1, 2. That will be our x-intercept. Let's look at the y-intercept. The y-intercept is -2. So this means to pass through -2 and reach that point. For now, this point is open. Okay. Now we go to the second graph. This one actually is a straight line, -4. It's a straight line. Okay. Now let's look at the last one. If you substitute 2, the answer is 0. So it's at this point. If now we look for y-intercept, our y-intercept is 4. 1, 2, 3, 4. This is our y-intercept. And our x-intercept, if we equate this, so this will be is 2. Our x-intercept is 2. So because we are plotting this graph greater or equals to 2, so this one now will be solid. Okay, and then it goes down up to infinity. So this one is our y-axis, this one is x. So we are done. We have managed to plot this type of a graph. Okay. So you should be able to plot this type of graph. I tried to go through step by step, looking for the value at the restricted domain, and then check the y-intercept, the x-intercept, and so on. So you should be able to plot this type of graph. Okay. So I wanted also to discuss transformation. But instead of discussing transformation, I think I'll do that in the next class. Let's take 2 more problems under this one. I'm going to take them from my notes here. Under the same topic. We're still under the same topic. I'm just adding 2 more problems. Okay. Now let's say I give you this function. Fx equals to, let's say negative x, provided or for 0 less than or equals to x less than or equals to pi. And this is equals to x for 0 less than or equals to x less than or equals to to pi. The first one, let's make this one negative pi. Okay, now the first question I ask you to sketch one cycle. Sketch one cycle. Number two, just say I ask you to determine if the given function is even or odd. And the last one, I just ask you to, instead of 1, now you plot 3. Okay. So for Fourier series, the type of problems that we're going to get is this one here. Okay. Now, let's say if it was a Fourier series, I'll add this one here, period, and then I'll say the period of this function is f x plus 2 pi equals to fx. So you have all the information that you need now. Now I'm going to plot the first one. The first cycle, I'm answering this one. So this is the case. So here is minus pi, 0, pi. Okay. Now this is the y-axis and the x-axis. Now to answer this, we have plotted the first cycle. That's how it would look like. Now they ask you if this is an even or odd function. So you can clearly see that it's symmetrical with the y-axis. So being symmetrical with the y-axis, then it will be an even function. Another option is that you can, let's say this is the center of the page. This line here, the y-axis is the center. If we were to close that page or flip that page, if this point here and this point, they meet at one point when you close that page, then we can conclude that the given function is an even function. Okay, then number 2. So it's an even function. They ask you to plot 3 more. So to plot 3 more, so this will be minus 3 pi. And then the next one here, we need 3 pi. So you can even make your own imaginary axis here. So at this point here, it will be 2 pi. So it must reach 2 pi and go up there. This is negative 2 pi. So this point here, it will be 2 pi. So now we have plotted 3 cycles, 1, 2, 3. So this is a repeating function, okay? That's why I just wanted to show you why we have to cover them at the same time. Now, let's say now we are given another function here. Let's call this one ft equals to 1 minus 1. Then we can plot it on the same interval as that one, 0 less than or equals to t less than or equals to pi, 0 less than or equals to t less than or equals to what? To pi. And again here our period is still the same as the above one. Our period is still 2 pi. So t plus 2 pi equals to ft. Okay, now the questions are still the same as that one. We start by plotting the first cycle. Let's do that. Let's plot this one. So our function between 0 and pi is what? Is positive 1. It's just a straight line like this. So this is 1 and this is pi. Between 0 and minus pi, our function is minus 1. Now we have to answer, this is y and this is x. Now we have to answer, is this an even function or an odd function? The correct answer is that it's an odd function. Okay, it is symmetrical about origin. So now comes the second definition that I have given you of the page. If this was the center of the page and then we close, or we flip this, we close this, we will see that this point here and this point will be at a different point. They won't be at the same point. So that one clearly shows that this one is an even is an odd function. So this is an odd function. Okay. This is an odd function. Okay. Now you can be asked to plot 3 cycles. You just have to extend that and extend this one. Okay, I'll try to utilize the space I have here. Okay, or maybe I can plot it this side. I'm not forced to plot it that side. Okay. So from here to this point here, it will be, and then the center point. So let's say this is 2 pi and this is 3 pi. Okay. Then from this point to this point, this will be the case. And then from this point to that point. Hello, I'm coming. Okay, a few seconds. Hello, then let's complete this one. So I've plotted the second cycle from pi to 3 pi. So because of limited space, I'll just edit from this side. I'll just use a different color. So you can extend this one. Doesn't matter whether you put it on the right hand side or the left hand side. I just want to see those 3 cycles. So from 3 pi, I think it must be 5 pi. Must end at 5 pi. In the middle here, it will be 4 pi. So let's plot this. So we can even make imaginary axis. Okay. So I'm trying to make it clear. So from here to here, it will be this one. And then on top there, it will be that one. So now we have 3 cycles. The first one is the blue one, the third one, the green one, and the black one. So this, you can clearly see that this is repeated over a period of 2 pi. Like that, like I said. Okay, so you should be able to do this. So I'm going to end my class here. Let me stop my recording and then okay.